In order that we can calculate the performance level of any gas turbine engine, specific symbols are used to denote the pressures and temperatures at various locations throughout the engine. Some of these symbols are shown in this diagram. These symbols vary slightly for different types of engine. We've learnt that thrust is obtained from the reaction derived by accelerating a mass of air backwards, thereby achieving forward thrust. In accordance with Newton's third law, for every action there is an equal and opposite reaction. If we examine the formula, in our case the force we require is thrust, so we can restate the equation in this manner. When W equals the mass of air in pounds, V1 is the inlet velocity in feet per second, and VO is the exit velocity in feet per second. In the case of a turbojet running in a choked condition, there will be the addition of pressure thrust, which will give us this. The power of a turbojet can be measured as thrust. Thrust is displayed on either a P7 or an engine pressure ratio gauge, both of which are thrust gauges. The engine pressure ratio, or EPR, is the ratio of the pressure in the jet pipe of the engine, which we call P7, to that at the intake of the engine, which we call P1. The power output of a fan engine can be shown on a gauge which measures the ratio of the integrated values of the turbine discharge pressure and the fan outlet pressure to the compressor inlet pressure. The output of a turboprop is measured in shaft horsepower, or SHP, produced at the propeller shaft. The engine's torque, or turning moment, is proportional to its shaft horsepower. Torque is displayed on a torque meter. P7, EPR, and torque meters are all covered in engine instrumentation on this disc. Thrust equivalent horsepower, or TEHP, is the unit of power used to describe the power output of turboprop engines, and also some turbo shaft engines. In practice, there is always a certain amount of jet thrust in the output of a turboprop engine. The equivalent shaft horsepower of a turboprop engine is derived by adding its shaft horsepower output to any horsepower obtained from its jet thrust. Under static conditions, one shaft horsepower equals approximately 2.6 pounds of thrust. We saw from the earlier equation that thrust was proportional to the mass flow rate of air through the engine, and the acceleration we could impart on that air mass flow. Both the mass flow and the acceleration will be affected by changes in altitude, temperature and airspeed, which all have a bearing on the efficiency of the engine and therefore the gas energy available for conversion into either thrust horsepower or shaft horsepower. To be economical, an engine must maintain the ratio of its fuel consumption to either its thrust or its shaft horsepower at as low a level as possible. This ratio is termed the specific fuel consumption, or SFC, of the engine. Specific fuel consumption is measured in pounds of fuel used per hour per pound of thrust or shaft horsepower. The specific fuel consumption is determined by both the engine's thermal and its propulsive efficiency. The amount of thrust produced by a turbojet is proportional to its RPM. Engines which have either a single spool axial flow compressor or a centrifugal flow compressor, and some engines with a combination of centrifugal and axial flow compressors, have a linear relationship between their RPM and the thrust they develop. This linear relationship is shown in this diagram. Engines which have twin spool compressors have a slightly different relationship between RPM and thrust developed. This happens because optimum compressor blade efficiency and compressor ratio are designed to occur at higher RPMs that are normally utilized during the cruise, where the engine spends most of its working life. The relationship between RPM and thrust becomes non-linear, as shown in this diagram. This diagram illustrates that the highest 30% of the thrust is obtained with the RPM above 90% RPM. The ground idle HP RPM of a twin-spool engine is in the order of 58 to 62%, and the LP RPM idles on the ground at about 25%. In flight, these idle values will be higher because of the windmilling effect caused by the forward airspeed. In a high bypass ratio turbofan engine which is running at an idle power setting, the fan speed, or N1, is 25% of its maximum value. The engine will generate approximately 5% of takeoff thrust at this power setting. The different levels of engine power are nominated by the following terms. Takeoff thrust. Maximum thrust available from the engine. This power setting is normally time limited. Go-around thrust. This power setting can be the same as that for takeoff thrust, but it's normally a slightly lower value. Maximum continuous thrust. This power setting is the maximum level that can be used continuously. Maximum climb thrust. This power setting is equivalent to max continuous thrust and is selected to give the best angle of climb speeds. Maximum cruise thrust. This is a power setting below the value of maximum continuous thrust. Maximum cruise thrust can be used, for instance, if the aircraft has to climb more quickly than normal because of a terrain clearance requirement, or in order to respond to a request from ATC for a higher rate of climb. As aircraft altitude increases, temperature, pressure, and density all decrease. The thrust of a gas turbine engine depends upon accelerating a mass of air rearwards. If the density of that air, and thus its mass, is decreasing with increasing altitude, then the thrust generated by that engine must also decrease as the aircraft climbs. Most sophisticated gas turbine engines, which are fitted in aircraft, incorporate an element in the fuel control unit to reduce the fuel flow to match the reduced air mass flow in the climb. This assists in maintaining a constant engine speed for a fixed throttle position. The fall of temperature with altitude increase has a second effect on engine thrust. Because of this reduction of temperature, the air density does not reduce as much as it otherwise would, under the influence of the pressure drop alone. This, to some extent, compensates for the loss of thrust caused by the reduction in pressure. This compensation continues to have effect until the tropopause, which is at 36,089 feet. At altitudes between the tropopause and 65,617 feet, the temperature remains constant at minus 56 degrees Celsius. Thus, at these altitudes, the thrust is affected by pressure alone. This graph demonstrates that the specific fuel consumption remains almost constant with altitude increase. This is because the fuel flow reduces at about the same rate as the thrust reduces as the aircraft climbs. As aircraft altitude increases and the density of the atmosphere reduces, a turboprop engine suffers a similar loss of power to that of a turbojet engine. We showed earlier that the output of a turboprop engine is a combination of its shaft horsepower and any jet thrust that the engine can produce. These graphs show that at a constant airspeed, both the shaft horsepower and the jet thrust of a turboprop engine reduce with increasing altitude. The result of this is that the thrust equivalent horsepower, which is the combination of shaft horsepower and jet thrust, will also reduce with increasing altitude. This graph shows that the specific fuel consumption of a turboprop engine improves as the aircraft climbs to approximately 20,000 feet, but then it increases again as the aircraft climbs towards 35,000 feet. We've already noted that on a hot day the air density will be lower than the international standard, and thus, as we saw from the simple form of the thrust equation, the thrust developed by an engine running at a given RPM will decrease below the level it would attain on an ISA day. However, Because it's hot, the air is less dense, and this means that the load on the turbine, as it attempts to drive the compressor at that given RPM, is less. The engine will thus require less fuel to maintain that RPM. Or, alternatively, the engine will run more quickly if the fuel flow is maintained at the same level. On the other hand, on a day when the ambient temperature is below ISA, the density of the air will increase, and the thrust developed for a given engine RPM will also increase. The load on the turbine will have increased because of the increased density of the air passing through the compressor. So, to maintain the given RPM, the fuel flow required will have to be increased. Or, alternatively, if the level of the fuel flow is maintained, the engine will run more slowly. In cold ambient conditions, when the air is denser than ISA, the engine will develop its required takeoff thrust before the limiting compressor RPM and turbine gas temperature are reached. However, opening the throttle any further to take advantage of any extra thrust which may be available will have no effect because of an element of the fuel control unit called the power limiter. The power limiter prevents the compressor output exceeding a set maximum pressure, thus safeguarding the integrity of the compressor casing. Engines which have the ability to achieve takeoff rated thrust at less than full throttle when ambient temperatures are below ISA are called part throttle or flat-rated engines. From examination of the simple thrust equation, it would appear that, as the aircraft flies faster, if the exit velocity remains the same with an increasing inlet velocity, the thrust will decrease. However, we know from the air intake lesson that the engine air intake is designed so that as the aircraft forward speed increases, the ratio between the total air pressure at the air's entry to the compressor and that of static air pressure at the air intake entry increases. This increases the mass flow through the engine and the exit velocity of that air from the engine. This effect starts to make its presence felt as the aircraft speed reaches between 0.1 and 0.2 Mach. These graphs illustrate that as airspeed increases, the ram effect into the intake of a turboprop engine causes its shaft horsepower to increase, while its net jet thrust decreases. The overall effect on the thrust equivalent horsepower of these two changes is shown in this graph. This concludes the lesson on engine performance.